This is the How to Steal Bitcoin talk, as you might have noticed up here. So just briefly, to introduce ourselves, I'm Nick Zeeb. This is my colleague Daniel over here. And what we want to cover today is we want to cover Bitcoin and overview some of the attacks that have been carried out against the people, the software, and the protocol. And as we go along, we're going to go from less sophisticated attacks to more sophisticated attacks. And as we go along, we're going to sort of try and explain a bit about how Bitcoin works as well. So you get the two in one. Okay, so in case you know nothing about it, Bitcoin is an internet version of gold. That is the best way to think of it. It is fundamentally limited. There will only ever be 21 million Bitcoins found in the whole of time, in the whole of the world. And each Bitcoin is currently worth about $240 right now. So how can I use Bitcoin to pay for things? Well, here's a screenshot of someone using a wallet application on their phone to pay a merchant for a service they're providing here by scanning their QR code. That's all you need to do. You scan someone's QR code, and you can send them money. Now, this merchant has a little sign here that says they accept Bitcoin, so you no longer have to use dirty old government money over here. Now, the point about Bitcoin is that you can make any payment to anyone like this. They don't have to be next to you. You can be anywhere in the world and ask for someone to send you money. You can send money to anyone in the world for any amount for less than a cent within minutes. Also, the payments that you make are irreversible. They're like handing over cash. So let's have a look at how we can use that property to try and get hold of some of these. Well, as in most systems, as we know, the most vulnerable part of a system usually is found right here. So let's see if we can find someone who wants something for nothing and give them nothing for something. So here is an actual real scam that was run using Bitcoin called Crypto Double. And they market themselves as a place where if you give them money, they're going to double your money, guaranteed, in just 100 hours. Now, I'm sure all of you would look at that and go, holy shit, that is not legit, that sounds really dodgy. Well, good. Not everyone thought that way. Some people thought, brilliant, this is a really good idea. So if you looked into this a little bit and had a look at the FAQs, like, you know, how can you guarantee this amazing claim? You know, they would say like, oh, we're a bunch of like really advanced traders. Like, we really know what we're doing. We're going to arbitrage these markets over here. We're going to use our superior knowledge of what's going on. We're going to double your money. And if you said, okay, well, why do you only take Bitcoin or other cryptocurrencies like Bitcoin? They said, oh, well, you know, because it's cheaper for you to send it, we don't want you to have to pay credit card fees. But of course, because it's also irreversible, it makes it very useful for them. So if you'd invested your money in this, after a while, things started to go wrong. This is their Twitter feed. There were a few so-called stuck withdrawals. Don't worry about it, it's going to be okay. Then they claimed there was a highly coordinated and massive DDoS attack. But don't worry, our engineer handled it. So as you can probably imagine, this money never got to come back, and people lost about $500,000 in this scheme. So that's a very simple social engineering trick. Another way to steal Bitcoins is to make use of the property that Bitcoin is open source. Anyone can take the Bitcoin source code, fork it, make some minor modifications to it, and tell you that they have invented the next big thing. And if you guys are smart enough to get in early on, call it PROIDEA here, if you guys buy into this, I'm going to guarantee you're all going to be rich. This is going to be the next Bitcoin. And of course, this happens all the time. There's over 500 variants of Bitcoin and cryptocurrencies. Some of them are real innovations, don't get me wrong, but I think many of them are probably scams. This particular coin here was a coin that was launched supposedly on the celebrity of Kanye West. And after he said he's not supporting this project, they decided to use this picture instead. But yeah, so not everything that shines is digital gold. That's the message here. Okay, let's have a look a bit more into the software. So this is a screenshot of a wallet. Now, I apologize for this dot matrix projector that we're using here, but bear with me. This is a desktop wallet, and a wallet in Bitcoin is a bit of software that shows you what balance you have. So this user has only about 50 cents worth of Bitcoin. You have an address on the system, which people can use to send you money. And here is an address book where you have other people's addresses, and that's what they look like. And you can see here that you've got the Free Software Foundation, WikiLeaks, you know, other places you can send money to. And crucially, And what the wallet does is the wallet allows you to make transactions on the network. The wallet doesn't hold any bitcoins in as such. What it holds is a private key, and the private key is used to sign transactions as you. And anyone who has access to that private key can sign a transaction as you and move balances around the network. So you must keep your private key private, absolutely. If that doesn't happen, you can be in trouble. So let's make use of that property. How can we get hold of someone's private key? Well, here's a good attempt. This is a real phishing attack that happened in Bitcoin. It is an email that said, "Hello, David." Why not David? Most of the users are male. And if you can't read this, the summary is, can you please help me out here? I've got a Bitcoin wallet. My Bitcoins are stuck. Please, can you help me get them out? I've got 30 Bitcoins that are stuck in this address. In fact, if you looked at this Explorer site here, you would see there were actually 30 Bitcoins stuck in this address. And they were saying, "Oh, can you please help me? Here's my password. Can you please get them out for me and send them to me? Thank you very much." So the aim is to try and get you to click on this link to download their so-called password.
Yeah, so as you can probably imagine, clicking on that link doesn't actually give you access to 30 Bitcoins. Yeah, it gives you something like this, which could sort of be a password in a text document. The kind of suspicious-looking command prompt behind there maybe indicates there's a bit more going on. This is actually just setting up a persistent backdoor to allow the attacker to remotely access your machine and remotely access your wallet. And it's possible to encrypt wallets, but a lot of people don't do that. And if they do, then the attacker just has to add some keylogger and pick up your password from that. And this is just one little piece of malware. There's a lot of malware out there that's geared toward attacking Bitcoin. In 2013, this report came out last year, about 2013, where Kaspersky found that about 22% of the financial-related malware attacks that they were detecting were actually geared towards attacking people's Bitcoins or trying to steal people's Bitcoins. And this covers like a whole host of different types of malware. You've got the remote access tool that we just saw, and there's other pieces of malware which actually try to attack your wallet directly. There's one called Coin Thief, which one guy posted he lost about $14,000 to that particular piece of malware. It would actually masquerade as a legitimate Bitcoin-related utility to help you receive payments more anonymously. But it would, in the background, it would just interact with your wallet and send all of your funds to the attacker. And this property of pretending to be a legitimate utility is kind of common in the Bitcoin malware. Like it lets the attacker do some target selection. So the kind of people that are downloading these utilities are the kind of people that would have Bitcoins anyway. There's another one which posed as a vanity address generator. So that would be something that just generates a whole load of public-private key pairs so that you can get a more friendly Bitcoin address. The addresses in Bitcoin they're derived from the public key, and they're typically not particularly friendly. This is what an address looks like, but you can't really tell anything from that address about whose it is. This is actually the address for the Tails project, but it's sort of machine-readable and not particularly geared towards humans. So what you would do if you wanted to make a donation to the Tails project, then usually you would just go to their website, go find their Bitcoin address, and you're not going to type that out. So people will typically just copy, go to their wallet, and then paste it in there. And then when you hit send, you're sending the Bitcoins to Tails. Or that's how things should work. There's another piece of malware which does something kind of neat. You may have noticed that the address that was pasted there doesn't actually match the address that was copied. And this was some very simple piece of malware, which it had at least one guy sort of worried on Reddit. This was something that would actually pose as a Bitcoin-related game. It was like some RPG where you complete quests and you supposedly earn real Bitcoins as rewards, but really it just leaves something running in the background which monitors your clipboard. And anytime it sees something that looks like a Bitcoin address, because they're quite distinctive, it would just replace it with the address of the attacker. And because they're not very human-readable, most people are just going to paste it in and hit send and not realize that you're accidentally sending money to the attacker. And one of the neat things about this is it's not going after just one particular implementation of the wallet, because there's now a lot of different wallets. They vary between native applications or web applications as well. This is a popular web-based wallet. This one, I think, is the most well-known web-based wallet. It's run by blockchain.info. These guys actually started out as a site to allow you to view and navigate around Bitcoin transactions. So this is their navigator interface, and down here you can see these are the recent transactions in Bitcoin. And these are not just your transactions. This is not like your account history kind of thing. This shows all transactions that have taken place on the Bitcoin network. So one of the things that you need to know to understand how Bitcoin works is that to see how it differs from conventional currencies. Usually you would have some kind of token, like you'd have a dollar bill or a zloty that you can give to somebody, and then you're transferring some money to them. Otherwise, there'll be some kind of central authority, like a bank, for example, which will maintain people's balances, and you can ask your bank to transfer some money to somebody else. With Bitcoin, there's none of that. There's no physical Bitcoin tokens that you can just hand to somebody, and there are definitely no central authorities. What you have with Bitcoin is a public ledger. It's a complete list of all the transactions that have ever happened in Bitcoin. And because they're public, then everybody on the network, or potentially everybody on the network, will have a copy of this ledger. And because it's complete, it has every transaction that's ever taken place, you can use this ledger to calculate what balances are. So at any given time, you know your balance is the sum of all of the Bitcoins that have been sent to you, minus any Bitcoins that you've sent to somebody else. And when you want to create a transaction, when you want to spend Bitcoins, you say, these Bitcoins that everybody knows I've received, I'm now sending them over to this guy over here. And then everybody knows that that guy's balance has gone up and your balance has gone down. So if we take a look at a real transaction, on the left, we've got a transaction input. This is the bit where you're saying, those Bitcoins that you all know I've got, these are the ones I'm spending. In this case, the person's spending about 9.5 Bitcoins. And you can specify multiple inputs if you want. If this guy wanted to spend more than that, he could specify other transactions where he'd receive Bitcoins, and then he would have more to spend in this particular transaction. In this case, he's sending it to these 3 outputs on the right. So these are the transaction outputs. This is the destination addresses. And if we take a look at this one just here, you can see this 120 or 120 address is being sent about 2.36 Bitcoins. You can also see that it says spent. This person who the Bitcoins were sent to, they've already spent those coins. And because we have a complete public list of transactions, you can go forward and see this is the transaction where they're spending those Bitcoins. This is the 120 address with the 2.36 Bitcoins. And this is how the transactions sort of fit together. The outputs from one transaction make up the inputs to later transactions. So the way that you ensure that only the intended recipients can spend Bitcoins is kind of interesting as well. How that works is, say Alice wants to send 10 Bitcoins to Bob. She doesn't have to name Bob directly in the transaction. What she does is she actually poses a puzzle that only Bob can solve. And this is done using the Bitcoin's built-in programming language. So here Alice creates a partial program which is locking up the funds. Here she's sending 10 Bitcoins. So these Bitcoins are now locked up, and only Bob will be able to unlock them. And when Bob decides he wants to spend those Bitcoins, he creates this is the hash of Bob's public key. So this is what's indicating that it's only Bob who's allowed to spend them. And when he decides to spend them, he creates another transaction where he specifies some data which completes this program. And this program now can be executed. So when Bob creates this transaction, he will broadcast it to the network, and everybody will be able to execute this program in its entirety and verify that this is a valid transaction. And what this does is, Bob has specified a signature and a public key. The signature is signing the transaction that he's created with the private key that corresponds to the public key that he specified. And this public key must hash to the value that Alice specified in her locking script, in her output scripts. And if all of those things are true, then everybody knows that this is a legitimate transaction. These coins were in fact intended for Bob, and he has now spent them. So if we take a look at a real transaction, here, this is on blockchain again, and you can see you have the output scripts down there. This has got 2 output scripts because this transaction is sending to 2 different addresses. And this kind of program here, this is the same kind of program that I just showed you in the previous slide. This is the most common way of sending Bitcoins. It's called a pay-to-public key hash because it's got the hash of the recipient's public key in it. And these instructions here, the things starting with op, these are the primitives of the Bitcoin programming language. There's only a few that make up this kind of transaction, but there's a lot more opcodes in the language, which allows you to be much more flexible with the transactions that you create. It also lets you do lots of other kind of fun things. There's one interesting opcode called opreturn, which lets you embed arbitrary data in a transaction. So here we can see this transaction has an opreturn statement, which is just sending a message to you guys. And this is used for a variety of different things. There is like a proof of existence service, which lets you upload the hash of a document, and it gets embedded in a transaction. And you can then see, or anybody can see, that at the time that transaction was created, that document existed in that form. There's also a proposal last month from one of the people behind TLS for using opreturn to help in TLS certificate revocation, so you don't need to use certificate revocation lists, or like OCSP or whatever. But given that we can embed arbitrary data in transactions, there's a lot more fun things you can do with that. Because there's one very common mistake that a lot of developers make when they're building software, which is that they don't correctly identify user input. Usually developers think about input as being the ways in which users are actually interacting with the software that they're writing. It's the buttons that the users click or the forms they submit. But given that anybody in the world can embed arbitrary data, and it's now being displayed in a website, this is effectively input to this particular site. And given that, it was only a matter of time before somebody tried putting JavaScript in a transaction. This is a fairly benign example. It doesn't do anything now, but it used to look more like that, where it actually execute the JavaScript. And that's kind of a dangerous thing to do, to be executing arbitrary JavaScript in the context of a JavaScript Bitcoin wallet. Because there's a very simple attack here where you just send somebody some small number of Bitcoins and you include some JavaScript in the transaction. And when they see they've received some Bitcoins, they click on the transaction and the JavaScript executes and it transfers their entire balance back to you. So this example is from a while ago. Blockchain have fixed that. There's also now a 40-byte limit on the amount of data you can include in an opreturn statement. It's being increased to 80 bytes, but at the moment, 40 bytes is all you have to work for, or you have to work with. 40 bytes happens to be the exact amount to do that, though. You can embed external JavaScript through a URL shortener. If you're using HTTPS, it should really require 41 bytes, but if you just miss off the closing angle bracket on your script tag, then the browser is quite forgiving. It sees it as a minor development error, and it executes it anyway. So that's some of the things you can do with transaction outputs, but let's have a look at transaction inputs again. So I mentioned before that the transaction inputs, that's in the example I showed you with Bob, he specified a signature and a public key. And there they are. You can see these on blockchain. The signatures are actually produced using the elliptic curve digital signature algorithm. And I'm not going to go deep into the maths behind how ECDSA works. But the important part to know is that your signature consists of two components. There's these R and S values. And there's a random number M, which is used to make up both of those. There's also the private key K, which is used to make up the S value. And one of the rules of ECDSA is that you must never reuse the same value of M for multiple signatures with the same private key. If you do, one thing that will happen is that this R value will also be the same across multiple signatures. And that makes these signatures very easy to spot, because you can just look through a whole load of transactions that somebody signed. And if you find one where or more than one where the R components of a signature match, then you know it was created using the same value of M. And the other side effect of that is you can then take the two S values from those two signatures, and you can actually algebraically calculate the private key. So once the private key has been compromised, then anybody can go and spend your Bitcoins. So it is quite important to use a strong random number generator there. The value of M is large enough that any half-decent random number generator should never repeat values for M, but sometimes people don't do random terribly well. We can take a look at this transaction here. This has got two inputs. These are the two signatures. Those are the two R components, which if we zoom in on those, you'll see those are actually identical, which means these two signatures were produced using the same value of M, so the private key is now compromised. And this actually seems to happen, it seems like about once a year. This is an example from 2012. In 2013, there is a weakness in Java Secure Random, which led to the Android Bitcoin wallet repeating M values, which allowed some people's private keys to be compromised. Then last year, blockchain had a similar issue. They were actually trying to update their JavaScript wallet to increase the entropy pool they were using, and they accidentally reduced it to 1 byte. So they were repeating M values very often. In this case, when this started happening and these transactions with the repeated R value started showing up on, in the ledger, there was one guy called Yoho who actually spotted this was going on, and he swept up more than $300,000 worth of Bitcoins from compromised private keys. And then once blockchain fixed the issue, he gave it all back. So that was kind of nice. And this is a problem that doesn't just affect Bitcoin. It's anybody who's using ECDSA can be potentially vulnerable to this kind of attack. And in 2010, this is the same technique that the group Fail Overflow actually used to crack the private key that Sony used for signing code for the PS3. In that case, Sony's random number generator just always returned the same value, which made it quite easy for them. The slide I showed you earlier with the maths on it, I actually took that from their talk they gave at Chaos. And yeah, this is one way that private keys can be compromised. Like private keys, obviously, it's quite important to keep them private, which does mean that if you happen to be on television, don't hold it up to the camera to show people what a private key looks like. The headlines that follow that are kind of inevitable.
Okay, yep, that's good advice, Dan. Okay, so let's have a bit of a look into the actual protocol a little bit more. So we mentioned that Bitcoin is a peer-to-peer network. There is, like we said, there's no central node. There's no one bit of computing architecture you can take out to stop the network from working. It is like BitTorrent in that nodes freely connect to each other and they share the state of a network with each other. So at this point, you have what we call a distributed ledger. Every node on the network is aware that currently Alice is the holder of 2 Bitcoins and Bob owns 1. And everyone is in agreement about that fact. So let's have, if we look at what the nodes are actually storing, besides just the current state, they actually store the entire history of all transactions that have ever taken place, like Dan was saying. And they do this through a data structure that we can show here. What they do is they group about 10 minutes worth of transactions into a collection called a block. And that block will then be referenced by another block. These are the first transactions, and the next transaction that could take place are in another block. And there's a hash pointer that points back to the previous block. And this way, the structure keeps building up in an immutable ledger that cannot have its history changed by simply pointing backwards to the previous block using hash pointers. And this data structure here is called the blockchain. That's how Bitcoin stores its data. Okay, so how do new transactions get included in a block? How does that actually do that? How does that happen? So at any one point in the network, you have the last known block, the last agreed block, which is here. And you have a bunch of transactions that are not yet in a block. People have to simply broadcast them to the network. You can broadcast them to any node. And Bitcoin will use what's called a gossip protocol, where if I tell a message to you, say, you tell to all your friends, they tell to all their friends, and it just spreads like wildfire in the network. And everyone has a copy of everything that's been broadcast. So after that, there is a race that happens where all the nodes who attempt to create the next block, they're called miners, they will take all of the outstanding transactions, the unconfirmed ones here. They will add a random value to all the outstanding transactions, and then they will take a hash of all this data and create a hash value. And the Bitcoin protocol specifies that the first person, you can find a number here that will produce a hash value below a certain value called the difficulty. It gets to create a new block. And so what happens is people try lots and lots of numbers, and the first person to find something that works. Again, you can't predict the outcome, so you just have to keep going until you find one. In this case, say the difficulty was below 1,000. This is the first person to find a solution. What they do is they take all outstanding transactions like this, they group them into a block, and they add, crucially, one extra transaction in there called the block reward. This is how all new Bitcoins are created. All new Bitcoins are created by people mining and creating new blocks. This is how the currency is issued. Currently, for every person who generates a block, the reward is 25 Bitcoins. When the network started, the reward was 50 Bitcoins. And next year, it's going to be 12.5. So every 4 years, the reward halves, and it asymptotically approaches the finite limit of 21 million that will never be exceeded. Okay, so that's what mining is. So it's a distributed network, so it is actually possible that roughly around the same time, 2 miners on the network will find a valid solution to the next block. And what happens in that case? Well, in that case, you have what's called a fork. This happens about once a day on Bitcoin on average. What that means is that two people broadcast a new block, both of which build on the last good block here. And in that case, what happens is the Bitcoin network is temporarily split. What happens is everyone who sees this block first will try and extend this block by building on top of it. And everyone who sees this block first will try and extend this block. Now, what that means is that you essentially have a voting process happening on the Bitcoin network. People vote not with their identities, because Bitcoin mining and running the network is anonymous. Anyone is free to join and leave. You give no identity. What you vote with is your hashing power. So if, say, whatever, 70% of the hashing power is trying to extend this block and 30 this block, it is likely that the next block will be extending this one here. And the Bitcoin protocol says that people should always switch to trying to extend the longest blockchain, the one that has the most amount of work put into it. And because you know everyone else will do that, it is in your rational interest to do the same. Because if you try and extend this one, then this will become longer and longer, and people will ignore your blocks, and your rewards will be ignored. So just for your selfish interests, it is rational for you to orphan the block you're working on down here, to give up on it, and join everyone else on this side of the network over here. And that's how Bitcoin recreates the synchrony between the network in a distributed way. What this also means, in terms of how one could attack the network, is that if any single actor manages to amass more than 50% of the entire hashing power of the network, what you could do is you could split the blockchain from any point onwards and decide what you wanted to put in these blocks. Now, there are some limits to this. You can't put invalid transactions in it because the cryptographic signatures will no longer match and the network will ignore that. The one thing you can do is you can decide not to include transactions. So if you really want it, you could just produce empty blocks and basically censor transactions. This is called a 51% attack. It's quite expensive because the hashing power of the Bitcoin network is now enormous, but you could in theory do it. The other problem would be that it would be detectable. People would notice, oh, for no good reason, the miners are censoring transactions, something's wrong, let's go investigate. And the other nice thing about Bitcoin is that because it creates this immutable history, these block numbers, you can go back to any point in the Bitcoin history and restart the network from a block that we all agree. In fact, there was a security problem found early on in Bitcoin where the outputs of a transaction just had to add up to be the same as the inputs, but it wasn't checking for numeric overflow. So someone managed to create, several billion Bitcoin in a transaction by simply using the overflow of the outputs. And the way that was fixed was that the Bitcoin core devs got together and said, whoa, guys, stop the blockchain for a minute. Let's go back to the previous block that we know is good, and let's go from there again. That was many years ago. It was early on in the protocol. But because the transaction history is immutable, you can go back and restart any block. So in the case of 51% attack, people would probably just say, OK, SHA-256, which is the hashing algorithm Bitcoin currently uses, is compromised. Somebody has amassed more than 50% of the power in it. Let's change it to some other hashing algorithm. That's probably what would happen. But again, this attack is the most expensive one you could probably think of because it just requires so much computing power. So Bitcoin to work requires only that half the network is roughly being honest in what they're doing. Okay, so what does that mean for a single transaction? It means a single transaction has the following life cycle. When it is first broadcast to the network and not included in any block, it's what we call an unconfirmed transaction. That, within a few seconds, is sent to the entire network and everyone can see the transaction being broadcast. When the first miner includes in a block, and this will happen in about 5 minutes on average, because it takes 10 minutes to make the block and you're randomly going to broadcast it halfway through the process, you get your transaction included in one block. In Bitcoin terms, this is called one confirmation. If someone builds a block on top of that block, you get 2 confirmations and 3 confirmations and so on. As your transaction gets buried deeper and deeper into the blockchain, the chance that someone will be able to successfully fork the network in the way that we saw become lower and lower, exponentially so. So what does that mean for a merchant? Well, it means if you're selling someone a coffee, you can probably accept a single unconfirmed transaction because it's quite hard to fork the blockchain. If you're selling someone a Ferrari, you might want to wait 20, 30 minutes before you let them drive it off the forecourt in case they had some sort of ability to fork the network. So you can choose any amount of certainty you want in terms of accepting transactions. So if a merchant is being quite lax and they accept unconfirmed transactions, what could you in theory do to attack that merchant? Well, you can carry out something called a double spend attack. So in this example, Alice is the attacker. The network currently agrees that Alice is the only holder of the 1 Bitcoin that exists, and Bob and Kat have no Bitcoins at all. Now, in this example, Bob and Kat are merchants. And the connection between their two nodes is a little bit slower than the way that Alice connects to them. So what Alice can do is Alice can simultaneously broadcast 2 contradictory transactions to each of them. She can promise Bob her Bitcoin and promise the same Bitcoin to Kat at the same time. And if they accept those transactions that are unconfirmed, and Alice has managed to position herself in the network in this way that she can push her transactions directly to Bob and Kat, which takes quite a bit of analysis of the network and figuring out which nodes Bob and Kat are connected to, she could, in theory, do a double spend attack, and if Bob and Kat immediately go and send out the goods without waiting for any confirmations, then she could essentially get 2 of whatever she's ordering. Now, this is not a problem for Bitcoin itself because the next miner who creates a block out of this cannot include both these transactions. These transactions contradict each other. If you solve a block and put both of these in the block, everyone else on the network will ignore your block solution. Your reward, you will lose 25 Bitcoins because it's not valid. So it is not in your interest to do something stupid like that because you're putting real hashing power on the line. It's cost you some effort, some electricity to do this, so it's in your interest to act rationally. Like I say, this is not the easiest attack to carry out either because you need to know exactly how network is connected to the network and so on, but it could in theory be possible. So in practice, merchants will accept unconfirmed transactions if you're buying a coffee, but not if you're buying a Lamborghini. So, okay, let's have a look at the structure of a transaction again. So a Bitcoin transaction consists of 2 parts, like Dan was showing. Schematically, it's easy to think of it like this, that it is a transaction, a statement of intent saying, I want to send this particular Bitcoin I own to this other person, and you sign it with a digital signature, in this case, Alice. Now, we remember from Dan's slide, the signature has 2 parts, R and S. Now, unfortunately, in ECDSA, there is a slight problem that allows someone to take a valid signature, RS, make a minor mathematical mutation to the S component of the signature. You take the negative value and take it modulus n. It's not important that you understand what the mathematical transformation is. It's simply important that the way ECDSA works, it allows you to make a minor formatting change to the signature. When you do this, you can only change the way that the signature looks. You cannot change any of this. Change any of this and the signature no longer matches. All you can do is slightly change the formatting of the signature and it's still valid. So how could we use that knowledge to attack the network? Well, let's imagine this scenario. Let's imagine Alice is a Bitcoin exchange. And she has users, and sometimes the users want to take their money out. So let's say the user Bob wants to withdraw his 1 Bitcoin from the exchange. He says to Alice, please send me my 1 Bitcoin. She goes, OK, here you go, Bob. Here's a transaction I have signed as Alice to send you a Bitcoin. She tries to send this to the network. However, Bob, the attacker, has figured out which node Alice uses to connect to the network with. And what he does is he man-in-the-middle attacks Alice, essentially. At this point, when the transaction is being broadcast to the network, he goes and changes it. He goes and makes a minor formatting change to a signature. He negates it and does the modulus n of it. And now what happens is this message is still valid. Yeah, it's still all correct. It's just a slightly different formatted signature. So the network will go ahead and they'll confirm this transaction, and it'll all go through. Everything's good. Bob's got his Bitcoin. Now, what Bob does is he goes to Alice and say, hey, wait a minute, I never got my money. Can you please check on this transaction you've just sent out? And if Alice is foolish, she simply will take a hash of her transaction and go, oh, that hash, I can't find anywhere in the network. And if she's very foolish, she will not just rebroadcast the same transaction, because it should still be valid. She will generate a different transaction that references a Bitcoin that has not yet been spent and sends it again to the network. And guess what Bob does? Bob does exactly the same thing again. He then steals that Bitcoin. And if Alice is extremely stupid, she will automate this process and never check any of these complaints and just keep sending it over and over and over again. In fact, the kind of person who might do this would be like someone who would try and implement SSH using PHP. And they probably look like this. This was, in fact, the way that Mt. Gox claimed that their Bitcoins were hacked. They used transaction malleability in the protocol, and people stole money because they automated this process of just resending transactions over and over again. And it caused the loss of over $500 million worth of Bitcoin. So, yeah, that wasn't very good. I should point out at this point that many researchers believe that this is something convenient in the protocol that Mt. Gox has blamed the problem on. It's likely there were actually an insider attack, that Mt. Gox was actually insolvent long before this happened, but publicly the transaction malleability I explained is what they blamed for this problem.
Yeah, so if anybody is looking to steal Bitcoins, then exchanges are a pretty good target to go after. $500 million worth of Bitcoins. This is the largest ever Bitcoin heist in history. This one actually put Mt. Gox out of business. There have been other attacks against exchanges, though. Earlier this year, Bitstamp they're another popular exchange these days. They were hacked as well, not using transaction malleability, but they lost about $5 million. They're a bit more switched on when it comes to security, which is why they only lost this small amount. And they're still going. But let's go back and look at man-in-the-middle attacks again. So Nick mentioned how this can help to do transaction malleability attacks. And one of the problems with Bitcoin is that there's no inherent prevention for man-in-the-middle attacks. Like there's no endpoint validation like you would get with TLS, for example. It's a peer-to-peer network. You're connecting to random people on the internet, and you don't really know anything about them. So you could be connecting to anybody. And the way Bitcoin gets around the peer-to-peer bootstrapping problem, like the problem of finding your initial set of peers, is that there's this well-known list of DNS addresses, and when you start your wallet, it will resolve those addresses, and they always resolve to a long list of recent known good peers on the network. So that should give you a list of like 100 or 200 IP addresses that you can then connect to. So if an attacker is in a position to influence your DNS, or they can just get in between you and one of these IP addresses, or all of them, then they can ensure that all of your traffic goes through them. And that's one way of getting in the middle. There's another attack against Tor users. So going back to the transaction, the way you validate transactions, I showed you earlier there is that program that gets executed. There's a possible denial of service attack against Bitcoin where you repeatedly send invalid transactions, and you force the Bitcoin nodes to do unnecessary execution to try and validate them. That will always fail. And the way Bitcoin protects itself from that is that anytime you send more than 100 invalid transactions, your IP address will be banned for 24 hours. So the attack against Tor is to send a whole load of invalid transactions through the Tor exit nodes and get all of the Tor exit nodes banned. And then you run your own exit nodes and your own Bitcoin nodes, and anybody that's connecting through Tor will have to be connecting through either your exit node or to your Bitcoin node. And if they're going through your exit node, then the attacker can just redirect you to their Bitcoin node anyway. So that's one of the ways of getting in the middle of Tor users. The trouble with man-in-the-middle attacks is that aside from the transaction malleability thing that Nick was talking about, there's not really much else you can do once you're in the middle. You can prevent the user from sending transactions, but you can't really do anything to steal their Bitcoins. Their private key is still presumably secure on their computer. It doesn't give you any access to that, so you can't create transactions on their behalf. All you can do is stop them from sending Bitcoin, so it doesn't actually let you steal anything.
Okay, so in the last section of this, we just want to briefly touch upon some of the ways in which Bitcoin security is improving right now. So Bitcoin works through a bunch of, Bitcoin is upgraded through a Bitcoin improvement proposal, or a BIP. So here's one that's actually ready to go right now. This is to solve the transaction malleability problem we talked about. So there's already a known solution to this. Basically, it's a tightening up on the rules saying signatures can't be negative. There's a few other places in the protocol that allow similar things, like you can null pad some of the input arguments that Dan showed, but it's always the same idea. You can make a minor formatting change of transaction that doesn't invalidate it. That just changes the hash of it. And here is already BIP 62 is already the proposed solution of how to tighten up Bitcoin so this is no longer possible. This has not been implemented in the code yet, and it's not been released yet, but it is on its way to happening. So that's going to get taken care of. Another way that Bitcoin security is improving is that in a normal transaction, as we've seen, there's only a single signature here. So there's only one private key you need to compromise in order to compromise Alice's funds. Well, Bitcoin now also has the possibility of saying, funds can be locked up in such a way that you require more than one signature to do it. You can do like a scheme here where you say you have to have at least 2 out of 3 signatures on any transaction to be able to spend these funds. And what that lets you do is it lets you create independent private keys that have never ever been on the same computer, never on the same machine, that exist in different parts of the world, on different hardware, on different OSs. And when a transaction is created, Alice has to independently sign it, and so does Cat, before the transaction is valid at all. So that means the attacker has to compromise multiple points at the same time for this attack to work. In fact, this is the solution that Bitstamp went to after their $5 million hack that you talked about, where they use an independent organization called BitGo that will independently sign transaction and runs them through a bunch of risk profiling things. So you could do things like the other organization will only sign them if it's less than a certain amount, or if it looks dodgy because of the way that the patterns are happening. You're taking too much out in one day. It may stop it and go and phone someone up and say, wait a minute, this looks wrong. Are you sure you want us to sign this? Another way that Bitcoin security is improving is that people are starting to develop hardware wallets. The idea with hardware wallets is that you never ever let the private key escape the hardware. What you can do is you can plug this device into a laptop that could be compromised. The only thing a laptop can do is propose a transaction to the hardware, and you have to physically press yes or no to add the signature to it. There's various schemes that have not just buttons, they have pins, and you can use this in combination with multi-sig, where one of the signatures can only be produced on a hardware wallet, and the other one is on your Android device or somewhere else. Bitcoin hardware wallets can also look very differently. This is an example of a BitSIM. This is an overlay onto a SIM card that adds Bitcoin hardware functionality to any dumb phone. So that's an example. Another way that people have been talking in terms of improving the hardware is to use trusting platform modules. This is getting more common on hardware, where hardware comes with these modules that will only allow code that has a verified cryptographic signature to execute. And only under those conditions will this chip release the private key necessary to sign a transaction. So, yep, hardware is helpful there as well. Okay, so lastly, let's just go through the things we covered in the talk. This is a quick reminder of how we saw how to steal Bitcoins. The first way we showed you was simply to trick people to sending them to you. Always attack the human. It's always the easiest point. Another way you can do it is try and get someone to download some malware. Always a favorite. You can use cross-site scripting. You can take advantage of people having bad random number generators. You can just simply watch television until someone shows you their private key. You can try and amass more than half of the entire hashing power of the network, kind of expensive. You can attempt to double spend if merchants aren't waiting for transactions, if you have knowledge of the network setup. And you can exploit transaction malleability while it's still possible to do that before they fix it. Okay, thank you very much. Thanks for coming to our talk. We're happy to take any questions if you have any. Yeah. Do we have a microphone, or should I just repeat them? Oh, yeah.
Thank you, guys. My name is Dipankar. I work with UBS. I'm not very familiar with Bitcoins, to be honest. Well, I do have some knowledge now after this presentation, but a very basic question. If I have to use Bitcoins, as you said, you can use for transactions and stuff. How do I get these Bitcoins? Do I have to buy them from somewhere? You mentioned that there is no central authority.
Exactly, yeah.
So are there different vendors that you can buy from?
Yeah, so there's plenty of exchanges out there, some better than others, like we showed. I mean, we only showed you the ones that got attacked. There's multiple exchanges out there existing in different countries. You can sell things with Bitcoin. There's now, this is the Chancellor of the UK, George Osborne, using a Bitcoin ATM, where he's putting in worthless government money and he gets real Bitcoins out. So
one other option is always to steal them.
It was possible in the early days to mine Bitcoins. That's not that easy anymore. Bitcoin is modeled on gold, in that it's limited, but also on the way that gold is mined. In the early days, anyone could go to California, stick their hand into a stream and pull out a golden nugget, and that was CPU mining. And then it got harder. People had to use graphics cards to mine it. And as the mining process became harder and harder, and Bitcoin adjusted its difficulty to keep the blocks for 10 minutes, now you have to use special hardware, ASICs basically. So that's probably quite an expensive way to do it. So I would no longer recommend that to an average user.
Okay. All right, thank you.
No worries. Yeah.
Yeah. Can you talk about the value of the Bitcoin? It was $240 roughly. How does that work?
Okay, yep, sure. So here is a graph that shows the price of the price of Bitcoin. As maybe you guys can see, this was the great crash of 2012. Here it went from $35, it lost over 90% of its value, and crashed down to $2. So Bitcoin is like gold. Its price is set only by supply and demand. As far as I know, there are no dodgy bankers in London who fix this price every day. So yeah, it's simply how much we want to buy and how much they want to sell. Now, because Bitcoin is like gold, it has a slight periodic problem where people get very excited about Bitcoin and the price goes up, and then people look at it and go, oh my God, the price is going up, I must buy Bitcoin. And the price goes up higher, and people go, oh my God, it's going up even higher, I must buy more. And of course, that's not sustainable, and then eventually it crashes. And it's happened a few times now. This crash happened here when Mt. Gox finally collapsed. It's been a bit more stable around 200 now. The hope is that as Bitcoin advances, it will become more and more stable and less volatile, and probably end up looking a bit like gold. Gold too, fluctuates and has periods where it goes up, but it's not as wild and crazy and young as Bitcoin. Bitcoin's only 6 years old, so we're hoping it'll calm down and be like gold. But in the long run, it should appreciate in value simply because it's limited. Government money keeps being printed. Quantitative easing programs are very popular around the world right now. Bitcoin doesn't have quantitative easing. It's not possible. The protocol does not allow it. Yep. In fact, we have a picture of that somewhere, don't we?
Is there another question over here?
What else do we have? Oh, yes, this is what I was trying to say. Yeah, this is the supply curve of Bitcoin. We are around there.
Thanks. Understood that a lot of the security of Bitcoin builds on a big number of honest people on the network, especially miners. Mm-hmm. So what will happen when all Bitcoins have been mined? What will happen to the security model? Is this already planned, or will it have to adapt?
Excellent question. Yes, it's already been planned. So as we were alluding to in the early day, in the beginning of the talk, or halfway through, that in the beginning of Bitcoin, the block reward was 50 Bitcoins for every block. It's now been halved to 25, and it keeps going down, which if you add it up, looks like this. So in Bitcoin, there's actually 2 rewards you get for mining. We didn't mention the second. The second is transaction fees. You can include a small transaction fee. Currently, you need to include something like 1/10 of a US cent for any size of transaction to get it included in the blockchain. And the hope is that as we run out, as we approach the limit of 21 million in the next 100 years, that Bitcoin will be popular enough that transaction fees will be enough to cover the cost of mining. So we should see a balance from mining reward subsidies of Bitcoins being found to transaction fees taking over and securing the network by incentivizing the miners.
Okay, thank you very much for the lecture.
Thank you.